Good afternoon, everyone, and welcome to this new TNO webinar on Quantum Internet enabled by space. My name is Charlotte Postma. I'm in charge of the space strategy at TNO, and I have the pleasure to moderate again our session today. This is the second webinar we give on this topic, and last year's edition really exceeded all our expectations in terms of audience and ratings. I hope that this year we deliver as much value, and for this, I'd like to take you through a few items to make sure that you enjoy our time together. First, this webinar is recorded. Shortly after our session, you will receive a link and the video will be posted on social medias. Second, we are quite numerous today, so you are all muted, but you have the chance to submit all questions and comments in the chat. We will go through them at the end of our session. Based on the feedback of last year, we have planned a very long Q&A session. We think we can cover all of those live. In case it is not possible, we will come back to the remaining ones via email individually. Last but not least, we have a digital setup. So to foster interaction, we came up with 2 polls that will allow you to share opinion as we go. There is no wrong or right answer. The votes are anonymous, so I would like really you to feel comfortable to vote. With this, I think we are all set. It has been a year since we last spoke, and it has been for sure a very busy year at TNO in terms of quantum satellite communication. First, we heavily engaged in developing technology. We are a research institute, and we have engaged in a project called Laika, where together with European partners, we mature the different building blocks of quantum satellite communication. In Kicker, another project, we integrate different Dutch commercial quantum systems to distribute entanglement through fiber and free space. Last but not least, in QStar, together with Airbus Central, we have started to investigate possible architecture for a ground space quantum network. The second axis on which we have worked is to expand usage. We have joined 2 groups for this. The first one is a EuroQCI thematic working group on use cases, and the EGO1 user engagement group. And in Ficus, we have developed a tool where we have mapped the individual cybersecurity needs to the corresponding quantum flavor for QKD. Third axis of our action is indeed to make sure that we contribute positively to the European vision. For this, we are extremely proud to be about to deliver the design of the first EGO1 ground station that will pioneer the space part of EuroQCI. And second, just before the summer, we have joined the Kia Space group, and we really look forward to starting activities in that group. Last year's webinar was about evidencing if and when satellite links are enhancing quantum communication. And my colleague Gustavo highlighted that after 500 kilometers already, space links are beneficial for performance. This year, I propose that we zoom in the quantum repeater and that we have a closer look to the different quantum platforms, the different kind of quantum sources and memories, the different channels, and that we investigate also how can we leverage their variety. But before we dive into the quantum physics, before we go inside the wildness of all that techniques, I would like that we take a moment to reflect on why does this matter, why it is important to work on quantum satellite communication. Gustavo, the floor is yours.
Thank you, Charlotte. Thank you for the introduction. It is so exciting to be able to be here with you again. I really appreciate the audience for joining. As Charlotte just said, what we're doing is sometimes not very tangible. So I'd like to, again, contextualize quantum communications, and for that, I want to provide a very familiar analogy. I want to talk about mundane tasks, tasks that we do every day, and how we interpret them. How do we gauge how much time or how much complexity is involved in each of them. So brushing our teeth or cooking are things that we do, again, every day, and we have a certain idea. Maybe we don't know exactly how, but we have an idea how much time it will take us to conduct those activities. For instance, for me, for brushing my teeth, I can go to the bathroom, I can put my toothpaste on my toothbrush, I can open the water, and so forth, until my teeth are brushed. For cooking is similar, but with a few more tasks. I have to do groceries, select the correct ingredients, which recipe I'm going to use, but in the end, the combination of these individual tasks forms cooking for me. In fact, complexity theory does very similar approach to evaluate how complex a problem is. The difference is that in computer science, these minimum tasks correspond to addition of integer numbers. By counting how many additions are necessary to solve a certain problem, for instance, factoring, we can tell if it's an easy or a hard problem. And have we become very efficient in performing integer additions? With modern-day microchips, we are able to perform trillions of such computations in very, very little time. Even though we have this whole computational power at our disposal that ushered us into today's information society, we still have problems that are not tamed. And those problems sometimes are the most interesting ones. Now, in the early 90s, we discovered that there is a type of machine that could give us a shortcut, a complexity shortcut, to tackle very, very hard problems efficiently. That is what we call a quantum computer. A quantum computer uses entanglement as resource to perform computations and turn some very complex tasks that a classical computer would take a lot of time to solve into something a bit more tangible. Now, a quantum computer of the modern day looks something like that. It has a lot of cables, it has a cryostat, it fills an entire room with people dedicated to operating it. It's still not clear whether a single such quantum computer would be enough to tackle all the immense problems that we are looking at. But one thing that I like to highlight about this is that the quantum computer of the modern days looks very similar to another computer, the classical computer of the 50s. On the left, we have a picture of such a room filled with cables and connections and people operating it, and it was the classical computer. Now, I'm not sure exactly how the quantum computer will evolve, but if we take the classical computer as a reference, we know that it got smaller. And as it got smaller, we started putting it in all around. And not only did we put it all around, we also made connections between these classical computers. And by connecting these classical computers, we started looking into problems or solving bigger problems or creating more applications and use cases than we could have ever imagined with a single classical computer. Now, for a classical network of computers, the distances are not necessarily a huge problem because we have amplifiers. We can amplify the classical signals to breach through the high losses due to distance in our channels. For quantum networks, we cannot amplify quantum signals. But still, the blueprint of the quantum network of the Netherlands, for instance, it resembles a lot the first classical network of computers, ARPANET, in the United States. We have nodes connected to other nodes in smaller distances than a large connection over larger distances. So somehow we need to be able to cover these larger distances. Again, we cannot amplify, but we have a technology called quantum repeaters. Okay, for those who joined our first webinar, I'd like to go back to our picture of the future European quantum internet. Each of these red dots corresponds to a potential quantum node equipped with a quantum processing device. And the idea here is that we connect all of them. Well, how do we do that? Interconnecting quantum computers involves distributing entanglement, the resource that quantum computers use to perform their computations. In order to distribute entanglement, we can use photons. photons are extremely versatile quantum information carriers, especially those operating at the near-infrared and visible wavelengths, because they experience very low loss while propagating through the channels. Again, the channels can be either fiber or free space, as for instance, in a satellite platform. Now, if we have a source that can produce such entangled photons, we can position it at the center of our network and just send the photons to the computers, which, when they arrive, allow the computers to be entangled. Unfortunately, again, losses are a problem. Instead of doing this just with a single source, we can use a quantum communication primitive called entanglement swapping that allows us to subdivide these long distances into smaller stretches. These smaller stretches we call elementary links. And with entanglement swapping, we can chain them together. If we take a look into the elementary link, we see that it is built with a memory, a source, a Bell state measurement, and a channel. And this allows us to go through and distribute entanglement over long distances. Maybe it gives you a little bit more insight if we look at the version of entanglement swapping and entanglement distribution without the elementary link, just with sources of entangled photons and Bell state measurements. In this case, we need all the Bell state measurements to perform their measurements simultaneously and successfully, which, because of the extreme losses of the channel, is very unlikely. However, when you introduce a quantum memory, what happens is that we have access to a number of tries. Let me try to explain. Imagine that you're on the elementary link on the left, and your source is producing photons that get stored in a memory or sent to the Bell state measurement. After a certain number of tries, your Bell state measurement will be successful. That's great. It means that you can load your quantum memories with entangled states. Now, while these quantum memories are loaded, you can do the same on the elementary link on the right. In fact, you can attempt that a number n of times, which obviously will depend on your quantum memories. Provided that you have enough tries, eventually your Bell state measurement will itself be successful, and the quantum memories on the right will be loaded. At that point, you can extract the quantum states from the intermediate quantum memories, send them to the intermediate Bell state measurement, and upon a successful result, you have entanglement distributed between the edge nodes of your quantum repeater. Now, obviously, this is not exactly clear, but if we assign parameters, efficiencies, in fact, to each of these components, memory, source, Bell state measurement, even the channel, and also give a parameter n of the number of tries that your quantum memory allows you to take, we see very clearly that as the number of attempts increases, the performance of entanglement distribution increases significantly, to the point that we can bridge this distance and then connect our quantum devices.
So if I try to summarize and capture the key messages of what you just said, Gustavo, I retain that quantum communication matters because it allows to connect quantum devices, and connecting quantum devices is important because it will accelerate the development of quantum computing applications. To enable to connect quantum devices over distance, you need a quantum repeater, and a quantum repeater is a combination of a source, a memory, a detector, and a channel, which can be either ground or space. Am I forgetting something, Gustavo?
No, that's pretty much it.
Then I think we are all set to move to the second part of this webinar and dive into the different typologies of quantum systems, different sources, different memories, and what are their benefits and their drawbacks.
Perfect. So what we want to present to you in part 2 is somewhat a catalog of quantum systems. You want to populate your quantum network, but how are you going to do that? So let's go back to our picture of the future European quantum internet. Again, we have quantum information processing devices, channels, and elementary links, so we have it all connected. It might be in our very distant future that we have such a long distance interconnecting devices, but let's assume that's the case. Once we have that connection, what can these quantum computers or quantum devices do for us? Well, there are a certain number of applications that we have already identified. In particular, we can talk about distributed quantum computing when different quantum computers combine their power to solve even bigger problems, or distributed quantum sensing, where quantum computers connect directly to sensors to provide us even more sensibility in our measurements, or quantum key distribution, where quantum computers harness the power of entanglement to extract perfect randomness. Now, these are what we call use cases. And they are a few of the use cases that we already know, but they're not necessarily the entirety of all the use cases. There may be more coming in the future. But what do we want from these use cases? We want to extract requirements, because these requirements will trickle down to the performance of the elementary link. If a certain use case requires more rate or more quality of entanglement, that is the role of the memory, the source, the channel, and the Bell state measurement to provide it. So in other words, we want to make this connection, map use cases to platforms. But again, what's interesting about this is that memory, source, they can come in different flavors. In fact, there are different physical systems or platforms that can enact these functional roles. So what we are left with is a huge catalog of use cases, a huge catalog of platforms, and we want to connect them. How do we want to do that? Again, extract requirements from use cases, connect to the platforms, and then have the platforms tell us within which time frame a certain use case will be available. For instance, QKD is already something that we can perform. Distributed quantum computing is something that is in our horizon. But it's important that we understand from the platform and the technology developers how long that's going to take so we can have an honest argument with society. Okay, so in the end, we want use cases and platforms together. The problem is these platforms come in a long list. In fact, the list that I have here on the screen is by no means exhaustive. There are platforms that I'm not familiar with and platforms that we have not even identified yet. Not only that, but we have platforms and we have protocols, ways to use the platforms to use them as quantum systems. So you see, the whole list is extremely long. Instead of going into each one of them exhaustively, what we propose is to classify them based on a shared characteristic. In fact, let's ask a question. How does one create quantum coherence between a flying photon and a stationary excitation? In other words, how does memory and source interact? In this case, we identified two types, emissive and absorptive quantum systems. In emissive quantum systems, you interact with a single system that then produces a photon whose quantum state is entangled with the internal state of your system, so your stationary quantum memory. In absorptive systems, on the other hand, you have a source that produces pairs of entangled photons and a quantum memory that catches one of the photons. When this quantum memory absorbs one of the photons, its internal stage then becomes entangled with the other photon. The characteristics of these two types are such that, again, in the emissive case, we have source and memory coexisting within a single physical platform. On the other hand, for absorptive, we have a functional split, source on one hand, memory on the other. It's not exactly clear if that's an advantage or not, because if you have one single system, it may be easier to operate with that. But if you have two, you can individually work on them and boost their performance to then combine them again. So at this point, I would like to share with our audience a question. Do you see these two types of quantum systems suiting your application very well?
Well, maybe before our audience can actually vote, it would be very good to give an overview of what are the benefits and the drawbacks of both classes.
For sure. Now, obviously, we are classifying the numerous amount of platforms and protocols that are there. So we don't necessarily mean that these drawbacks and advantages are general, but by investigating their characteristics, we did identify similar characteristics. For instance, for absorptive systems, there is an increasing potential for multiplexing, the number of degrees of freedom that you can use to improve your channel capacity. For emissive systems, this is still possible, but very challenging. On the other hand, in terms of storage times, emissive quantum memories have much higher storage times with respect to absorptive ones.
So I think now you should be able to see the first poll popping up on your screen. I remind that there is no wrong or right answer and that the votes are anonymous. Feel really welcome to vote. While we are waiting for the results to appear, Gustavo, I would be very curious to hear from you if one or the other has benefits for space. Which one would you use for space applications?
That's a great question. I think that if we follow our first webinar, you will remember that this functional split between source and memory was actually quite beneficial. And that's because sources of entangled photon pairs have reached a very high TRL, or technology readiness level, meaning that they have been already demonstrated in a satellite platform. So in terms of near-term applications, I guess an absorptive system where the source can be placed individually on the satellite and the memory on the ground, that could have a significant benefit. However, we have satellites hovering at 500, 700 kilometers above ground, meaning that having high storage times is extremely important. So on one hand, the functional split is beneficial for satellites. On the other, the high storage times are also. So emissive and absorptive still are types that are not clear who is going to be on the satellite.
May I ask maybe, which one has your personal preference? Which one would you be more comfortable to work with?
Well, in fact, this goes back a bit to the beginning of my career. I started working with absorptive quantum systems, so they always have this special place for me. And if I make the connection with the projects that you introduced in the beginning, in Leica and in Kicker, we are indeed using absorptive systems, exactly because the idea is pushing the TRL of the technology towards space. So I think for the next couple of years, we're still going to be focusing on the absorptive case, and for that, it has my preference.
Okay. So in the result that I can see, in fact, the biggest part of the vote is for the answer C. People are a bit uncertain of which kind of platform is going to be best for their needs. We have 60% there. Answer B is a second choice, absorptive, okay, with 24%. And 10% goes for emissive.
Okay. That's very interesting. In fact, I'm not surprised at all by the fact that this is still not clear. As I said, we have a preference, but clarity is something that we are still working towards. And because exactly of that, we want to propose a new type of classification. But before we go into it, I want to remind you, that these two classes that we're proposing are not necessarily exclusive. So you can have on-demand systems that are emissive or on-demand systems that are absorptive. So it's just a different perspective from which to look at these quantum systems. But in this particular class, we're interested in knowing how is the stored quantum state made accessible to the quantum network. So your memory is storing your entangled states, and you're the network operator. How do you extract them? In the on-demand case, the analogy is that of a safe. You open the safe, you put your quantum state in the form of a photon. The photon is absorbed, so your quantum state is stored. And at a certain given time, you type in your password, open the safe, and the photon comes out carrying your quantum state. The idea here is that whenever the safe is closed, no other photons can come in. This is different from the fixed time systems where a photon comes in and it's like a drawbridge. The drawbridge is open, so the photon is queued in with the other photons coming together. Eventually, the drawbridge at a fixed time will close and the photons will come out. Again, the different characteristics tell us that the on-demand system has an access whenever needed, and the fixed time is always available, meaning that you can send as many photons you want. It's going to be queued in this little traffic jam behind the drawbridge, but when the drawbridge closes, all of them come out. I think at this point it would be interesting also to engage with the audience and ask them if these two types fit their applications best.
But maybe before we go in the vote, you can remember or remind to the audience what are the benefits and the drawback on both sides.
Absolutely.
Or why should I select the on-demand and when should I select at fixed time?
Yeah. Again, this is a more generalized remark. It's not true for necessarily all the platforms, but what we identify is, again, there's a distinct difference in storage time. The on-demand types are generally much higher storage times, while the fixed times have limited storage times. On the other hand, because of the characteristics of the on-demand, you can only have one quantum state stored at any given time, while for the fixed time, it's a continuous storage. Continuous in the sense that you generate photons, you send them to your memory, and the memory will take care of them.
So it's time for you maybe then to vote. Again, it's totally anonymous. I think you can select your preference for which class of quantum system best suits your applications. And meanwhile the people are voting, Gustavo, same question there. Which typology is better for space, according to you?
Great question. So I think that we have to remind ourselves that the satellite is a moving platform. So it's going to be going around the Earth. And not only that, weather is also a dynamic variable. So imagine that your quantum state or your satellite is holding on to a quantum state. What it needs is a window of opportunity where the weather is great, there are no clouds, and there is a ground station available to receive that quantum state. So because it needs to be this kind of window of opportunity, I do believe that the on-demand type would have the preference, simply because whenever the satellite sees the opportunity, it puts in the password in the safe, gets the quantum state out, and connects.
Is there any of the two that you prefer yourself?
Not necessarily prefer, but I would say that the continuous storage operation of fixed time systems is extremely valuable. The fact that you don't have to wait until you emit your photons, you can actually generate photons at a very high rate, is extremely important. The problem is the limited storage times. So if at any point we could increase the storage time so that we can combine the continuous storage plus a high storage time, that would be extremely valuable.
I see, in fact, the result there. In this one, we do have a winner. Our audience has a 46% vote in favor of on-demand and 18% at fixed time. We still have more than 30% voting for, well, saying that they don't know yet which one is going to be most suitable for their applications. And we have 3% that think that this will never work.
Well, I do understand the 3%.
You do?
Well, I do. It's something that it's not happening right now. So it's very hard for us to tell exactly which one to choose when, yeah, the evidence of it ever working is not present yet. We have a lot of demonstrations coming in, but yeah, I do understand them. And I hope that we can change their minds.
Let's see this. If I try to recap this second part of our webinar, I retain that there are two ways to classify quantum communication systems: emissive versus absorptive, and on-demand versus at fixed time. And there is no winner. Each type has benefits and drawbacks. So when it comes to choose a quantum platform, the real driver of choice is going to be the use case. But at this moment of time, we don't have yet the kind of lookup table, the exact mapping of which quantum platform for which use case. And I understood also from you that for space, absorptive platforms are going to be the easiest one to start working with on the immediate term, because the source in space has already been demonstrated. On the longer run, emissive ones have an enormous benefit because of the increased storage time. And for the second typology, very likely on-demand will prevail. Am I forgetting anything, Gustavo?
No, you're not. In fact, a very good summary. But I just want to mention that, again, to make it very, very clear, these types are types that or classifications, sorry, they are not the only classifications that are possible. They are tools that we use to make our analysis a bit more tangible. Again, the problem is a very complex problem. So we need tools to make them simple, to try to approach them efficiently.
I think now you are going to take us on a planet where the national hobby is to mix, to combine, and to interface.
Correct. So now that we've contextualized quantum communications, and we talked about the different flavors of platforms. I bring you back to the European Future Quantum Internet, where we have channels that are equipped with fibers, channels equipped with a space connection on a satellite, and all these connections are based on building an elementary link that can be concatenated with another and another and another to implement the quantum repeater, and finally get the connectivity between the quantum devices. Now, not only do we have this flavor of the channel type, fiber or space, we also have the flavor of platforms. We have on-demand, we have at fixed storage times, we have emissive and absorptive. We must not forget also that on the satellite we have choices of such platforms. So, okay, you're faced with this problem and you want to build your quantum network. How are you going to approach it? Are you going to choose one and go with it? Or are you going to mix and match? Well, this is what we call a homogeneous versus a heterogeneous design. In a homogeneous design, you pick one platform, let's say emissive or absorptive, and obviously you have to have one facing the other, but the photons that are emitted can go directly into a Bell state measurement, and there we're going to have the successes of our entanglement swapping operation. It's kind of straightforward because the platforms are the same, so their interfaces are simpler. If we go for the heterogeneous design, we have platforms that are not necessarily operating at the same parameters, and then interfacing them becomes quite hard. What we really want for the heterogeneous design is some form of a hub or an adapter that can bring in each of these systems and platforms and connect them at will. The problem with these interface mechanisms is that intrinsically they will add inefficiencies. So what we have to ask ourselves is, by combining these different platforms and trying to compensate drawbacks with benefits from the others, do we still have a better performance overall, even when the inefficiencies are accounted for? So I was very fortunate to be able to participate in a study a couple of years ago where we tried to simulate and evaluate the performance of a quantum network that was heterogeneous. In this case, we opted to use absorptive, emissive, and on-demand systems. In fact, this was translated into the NV Color Center, the rubidium cold atom quantum memory, an AFC quantum memory, and an SPDC entangled photon pair source. By combining these and evaluating the parameters and performance that have been depicted in literature, we were able to get a picture of what would be the heterogeneous versus homogeneous network design currently, to this day. And what we see is that indeed the inefficiencies of the interfaces with the performance aspects that we see right now in literature is not very good for the heterogeneous case. We still have the homogeneous design with a much better performance. So we took a little approach of saying, imagine that in 10 years, we improve all our efficiencies by 50%. All these systems would be 50% better. In that case, we do see that there is a regime where heterogeneous quantum networks can actually outperform homogeneous. And I should say that this is for a very specific case of heterogeneous network design, including these platforms. We have not done an exhaustive comparison taking into account any type of systems such as this. So these regimes are very important because they represent what we should go for in the future. Now, combined with that, the benefit of a heterogeneous design, we also have, if you remember from the previous webinar, the indication that space also has a regime above 500 kilometers where it is beneficial. So this tells us that combining platforms and combining channels is extremely important.
Does this mean that we need at every node both channels, ground and space, and all the variety of platforms?
Well, I guess that could be one interpretation of the problem. Just shove everything into every node in your quantum network. That would definitely solve the problem, but maybe not in the most efficient fashion. And that's because it's very complex to interface them, and it's also very costly. So I like to bring us back to the use case. different use cases, again, will require different platforms. So instead of just creating quantum networks that are exhaustively complete with all the platforms and all the channels, instead, let's look at what we're trying to solve. Which is the use case? Is it QKD? Is it distributed quantum computing? And which platform will give us the better performance? And then we focus on the interfaces and build those interfaces. Now, one comment. In terms of technology development, I think all the different platforms are extremely important, and we should keep looking into them and looking for more of them. This is very, very important. But there's a difference between developing the technology and actually building our quantum network. For building our quantum network, let's select a few and really push their performance.
Very clear. So if I can do an analogy a bit between interfacing and the normal world, if I take the one of crops, I see this quite similar. We have some crops, some varieties that are very good for yield, but resist less good for the pests, and vice versa. Some varieties are very sensitive to disease, but have a very high yield. So when you try to maximize this and minimize the risk, you want either to hybridize your crops or then seed different variety in different fields to make sure that you mitigate the risk.
Yes, and indeed, variety is a very important aspect of it. As we saw in the previous webinar, and it's also true in this case, by having not only a single satellite, but many different space platforms, many different ground stations, different nodes in the ground with different platforms, allows us to choose the best path. Which ones can we use? So diversity and variety is really key for the design of a quantum network. Now, before we go into the conclusion, I like to just highlight the fact of, or highlight the complexity of integrating these different platforms. And this comes from the fact that in an elementary link, we need the photons emitted from the sources or the memories from the different quantum systems to interact in a Bell state measurement. Now, the Bell state measurement relies on a process called two-photon quantum interference. And without the details of it, it relies on the indistinguishability of the photons, which is a big word, but it only refers to the fact that the photons need to be completely equal. Now, being completely equal for a photon means that all the degrees of freedom of the photons need to be the same. And the problem is that the photons have many degrees of freedom. In fact, they can be operating at different wavelengths. They can be encoded in different encodings, such as phase or time bin. They can also have different polarizations, spectral modes, and temporal modes. So again, you have to imagine that each of these quantum systems, each of these platforms need to talk the same language, which goes into all these translations. And there are even more than that. So that's why interfacing them is such a complex task.
If we try to capture all this again and think about the key takeaways for this part, the overall goal is really to try to increase performance and serve a wide variety of use cases. So to attain this goal, the future quantum internet should hybridize space and ground links and mix different types of quantum platforms. Yet, mixing together different kind of quantum platform is not easy because they have different physical properties, and the complexity increases even more if you add the space link to the equation. So an enormous topic of research for the next years is going to be, for sure, this question of interfacing. With this, we have covered a lot and we are reaching the end of our webinar. As a conclusion, I would like to highlight the fact that this question of the right quantum platform and the right quantum channel is a central one. To be sure that we deliver relevant innovation for the space part, to make sure that eventually the space and the ground are compatible, we need to take a step back. We need to understand the bigger picture. And for this, I think we really need to go beyond the classical divide between ground and space and join forces to study together the user needs. I believe this will be the next chapter of our journey at TNO, and I think it will happen via collaboration. With this, I thank you very much for attending this webinar, and I'm very happy to kick off the question and answers. We have a first question from Bob, who is asking, what is the role of classical networks in this story? Will there be a parallel network, or can we reuse the normal internet?
Thank you, Bob, for the question. Extremely good question. I'd like to start saying that there is no quantum network without a classical network. The problem of synchronization of the nodes, of control and stabilization of the quantum channel is a problem for our classical network. Now, because of that, in general, we try to think of them as complementary. The classical network will take care of stabilizing everything and synchronizing everything and performing all the communication, and the quantum network will simply send photons around, store, or re-emit them. The fact is that many of the channels, as you seem to indicate in your question, are similar. You can use fibers to transmit classical signals. You can use fibers to transmit our photonic qubits, and the same is true for space. Now, why not use both? Well, in general, there's a little bit of a problem because the classical signals that we transmit are overloading with photons, so they introduce a lot of noise. Obviously, a lot of work has been done over the past 20 years to be able to create a channel, a fiber or free space channel, that incorporates both signals, both the classical and the quantum, into a single physical channel. So yes, classical networks are extremely important for, again, synchronization, stabilization, and communication of, for instance, the successful results of the Bell state measurement, or better yet, when to extract a quantum state from our on-demand quantum memory. Not only that, these signals can propagate through the same physical channels, but we have to filter them out so that we don't harm the quantum beams.
Thank you, Gustavo. We have another question. Which system is suitable for distributed quantum computing?
Okay. What we haven't maybe talked about in depth during the initial blocks is that the flying photons that we use for quantum communications, those operating in the infrared or near-infrared and visible wavelengths, they are great for carrying quantum information over long distances. Now, they are not exactly the same kind of excitation that a quantum computer uses. So there needs to be an interface between all this quantum repeater technology and finally a quantum computer, something that translates the quantum states of our flying photons into something that the quantum computer can interpret and operate with. There's a name for this type of technology. We call it quantum transduction. It's something that has not yet been demonstrated to the point that we can actually connect a flying photon to a quantum computer, but there are several significant works being published in literature right now and startups focusing on this technology. So I guess the question is there a particular platform right now that will interface better with a quantum computer? That's not exactly the case because we don't have a transducer yet. But whenever we have one, that transducer will most likely have a preferential platform to interact with. And then that platform will definitely be a must-have for our quantum network design. And then the interfaces to that, from that to the rest of the quantum repeater are going to be extremely important.
We have a question. Can geosatellite be used, and how does this change some of the characteristics or some of the dynamics and the physics?
Okay, so geostationary satellites hover above us at an altitude of about 36,000 kilometers. It's a lot of distance. They can definitely be used. The only difference or the only caveat is that the sources or systems that are inside the satellite must be extremely powerful. So you need to generate a lot of photons so that they can, or at least one of them, can survive the long distance propagation and reach the ground. With the current systems that we have, most sources that can produce photons at the rates that would allow geostationary satellites to be used as a platform, are unfortunately very broad in wavelength. It means that they have a lot of spectral modes. And a lot of spectral modes doesn't really go well with a quantum memory. In fact, quantum memories prefer very narrow spectral modes because their transitions are very well defined. So yes, a geostationary satellite could be used, but again, we have a big interfacing problem again, because the photons that are coming from the satellite are going to be very broad in wavelength, but the memories are very narrow. So how do you interface them? Ideally, either you have a memory that is as broad as the photons that you're emitting, or you can generate sources that are more narrow. And here we go into the discussion of multiplexing. How can we improve the whole channel performance, the channel capacity? And yeah, that's a bit of a complex issue, because with such a broad emission wavelength and narrow absorption wavelength of the memories, multiplexing becomes quite challenging. So to answer your question more precisely, yes, geostationary platforms can be used. There's nothing that changes in the physics, but there are very important considerations for, again, the interfacing.
We have a question here. How is TNO picking up their favorite quantum platform, source and memory, and what is their motivation?
Great question. So I guess there are two ways that we do this. The first one is by having Charlotte and others interact in the use case groups and allow us to, the scientists, to understand what is needed. Again, a mapping between use case and platforms through requirements. And with that, and our knowledge, our search in literature, we can identify certain platforms that would be able to enable that given use case that Charlotte provides us. That's one way. The other way is interfacing directly with companies around us in our ecosystem. So if we have a company that develops a certain type of source or a certain type of memory, we evaluate whether we have the familiarity required to understand that system and interface systems around us that can talk to that. So with this too, looking at the use cases that are thought of and the technologies that are currently being developed in our ecosystem, we can then evaluate, is there any technology development that we can do that will fulfill a missing gap there?
We have another question. For the fixed-time quantum memories, how do you disentangle which photon is which? If you store multiple photons, which is only entangled with one other photon in another quantum memory, how do you make sure that you extract the right photon for your subsequent Bell state measurement?
Okay, that's a great question. As I said, the photons, they get stuck in this little traffic jam because the drawbridge is open, right? That's the analogy. The fact is, once the drawbridge closes and the photons can come through, they will come out in the same exact order that they came in. So you can associate photons to times. You know that this photon came first and another photon came second. You know exactly at which time they came. So by synchronizing the nodes, you can tell which photon is entangled to which.
How would you deal with different photon arrival times with fixed memories?
I think that's a very similar question. Yeah. Again, it highlights the importance of a very well-designed classical network, because only with a very well-designed classical network we will have the necessary precision of timing to be able to tell exactly which photon arrived at which time, and then assign photons from one side of your elementary link to photons from the other side.
What is the quantum bit rate of such a quantum internet connection?
Okay, that's actually a great question. I'm not exactly sure to which quantum network the person that asked the question is referring, but I'm going to assume a network that we showed on the screen. The fact is, even with the best performance that one of these platforms could give us today, we are not there yet. We are not at the point where we can really perform or enable any of the use cases beyond QKD. So QKD right now is really the only use case that we have available to us. We have sources that can produce enough photons to compensate for the losses and then extract randomness from it. So the qubit error rate is generally the way that we assign a certain quality to the entanglement because it combines not only the rate at which you're generating entanglement or the photons, but also the quality of the entanglement. The Q-bears that we have seen in very, very long systems, I think the one that is longer is the Micius mission from China. I think they achieved 1,200 kilometers with a qubit error rate of 2.5%. So extremely impressive result, again, from a satellite platform with a very powerful source built in. In fibers, the rates that we can achieve, or a qubit error rate that we can achieve in fiber with entanglement-based solutions is very, very low. There has been a recent demonstration in the Brooklyn quantum network with a Q-bear of below 1% with rates of key generation above 10,000. So very impressive results coming in, and I think this is only going to improve over the next few years.
We have a question about timing. You mentioned that classical networks are in charge of synchronization of the nodes for the quantum network. Does it mean that speed is limited to classical latencies, or is there a way to synchronize with quantum effects?
Okay, that's a loaded question. And I say loaded because there are certain proposals on how to synchronize systems beyond the capacity of classical synchronization using entanglement distribution. However, these proposals require rates and qualities of entanglement similar or even better than those required for distributed quantum computing even. So yes, even though there are proposals, it's also important to highlight that this is maybe a couple of years in the future. Now, to answer the first part of the question, yes, latency, classical network latency, is an extremely sensitive issue for quantum network synchronization. And that's why there are certain protocols that do not necessarily go through the server network of our internet. It's maybe you're thinking about the internet, and then you have to have the communication between the servers, and that includes a lot of latency. For the quantum network, we are probably going to need a dedicated classical network that operates beyond the actual internet that we use to go into the World Wide Web, so that we can deliver much better precision.
We have another question. If there are repeaters on the ground, or there will be, what is the reason for using space links?
Well, that's an invitation, actually, because in our first webinar, we discussed exactly that question. In fact, the theme that we approached there is, imagine that you had all the connection of that future European quantum internet, and imagine that you could choose between ground with as many elementary links of a quantum repeater you want, or you could choose to go through a satellite. And what we saw is that even with quantum repeater technology on the ground, there is a moment where satellite platforms actually overcome the rate achieved. So to answer your question, it is going to be required above a certain distance. And if you want to know a bit more, I invite you to join our first webinar, which is recorded, and you can watch it. And also, we have a recent paper that has been published on that same topic. So yeah, an invitation for you to check it out.
And you can find the link to the paper on our website, tno.nl. Which specific quantum programming language will be preferred for implementing the protocol for quantum networking?
That is a very good question. I have to apologize to the audience. I am not the best person to be asked which programming language is the best. I would assume that a programming language that has no barriers, a programming language that is free of use, that everybody can have access to, because building a quantum network is not going to be something that one research group or one person is going to do. It's going to require a community, and a community that is not relegated to research centers and startups and organizations such as TNO or academia. It also requires people to develop and think about it together. So the more open source you can be, I would imagine that programming language will be the most used, and therefore the choice, the standard.
you say that indistinguishability is needed. If you interface with different platforms, do they all need to be compatible with each other?
Not exactly. You don't need, if you have, for instance, a chain of platforms that are interfacing one to the other, you don't necessarily need one to be completely indistinguishable from the other and from the other, because you can have interface elements in between. So to give you an example, imagine that you have a system operating at a certain wavelength. You want to interact with another system that operates at yet another wavelength. You can use something called quantum frequency conversion to make them compatible. Okay, great. So now platform 1 is compatible with platform 2. Now, here comes platform 3, which, even though operating at the same wavelength as platform 2, uses a different encoding. Now, you don't want to use quantum frequency conversion here because it's not going to do anything for you. What you need is a qubit encoding mapper, something that transforms, for instance, a photonic qubit encoded in polarization into a photonic qubit encoded into time bin. So again, knowing exactly which platforms you are going to use and the physical characteristics of these platforms is extremely important to understand which interface mechanisms you need between them.
Another question, would a quantum-based intra-satellite link be possible in the scope of 10 years? For instance, to synchronize future optical clocks for GNSS satellite without a ground segment?
I really like this type of questions because it gives us a very clear timeline. I'm not sure if I'm going to be able to successfully answer it, but I like the fact that you're looking for something in 10 years. If I look at the previous 10 years and where we were 10 years ago versus where we could be in 10 years from now, I would say that inter-satellite communication or quantum communication is indeed a possibility. I see that the technology readiness level of sources on board satellites is increasing dramatically. More and more missions of a quantum payload are being created, more startups dedicated to this, and big companies also investigating that. I don't think it's going to be I don't think it's going to take a long time until one satellite, one design is extremely successful, and then making more is just a matter of system engineering it and mass producing it. So again, it goes back to variety and diversity. Once we have a design that fits a use case, we can replicate that design and fill our orbit with quantum payload carrying satellites, and then we're going to have inter-satellite communication. 10 years seems to me a very good timeline for that. I don't want to give you an answer that you will interpret like the truth, but I would say it's very likely.
We have another question. Do you think we can use the quantum internet to play Grand Theft Auto 7?
That's a question that I'm asked several times already. If you had asked me this question a couple of years ago, I would say absolutely not. There are no games that you can play over the quantum internet or with a quantum computer. But that's a bit small, it's narrow, because we interpret games in a very specific way. It's the same when the first classical computer came about and someone said, maybe we could play a game here. And people were like, no, games are like football or basketball. And then now we have all the video games taking over the world. And I think maybe a similar approach could be taken here. I'm not saying that we're going to run Grand Theft Auto on a quantum computer. I don't think that's going to be very useful. But there might be another perspective or a different type of game that actually uses the properties of quantum mechanics and therefore needs to be run on a quantum computer. It's probably going to be a very different game than what we have access to now, but yeah, I see that possibility very well. Another thing that we can think about is, imagine that you have a quantum computer that is very small and you can have it at your place. Maybe your game, it reached a point that it's so complex that some of the tasks that it's trying to solve actually are more efficient on a quantum computer. So your quantum computer could act as an accelerator, much like the GPUs or graphical processing units have been used for over 40 years now. It's a dedicated platform to solve specific problems that could improve your experience in playing games, for sure.
What is the difference between using a delay line or an absorptive memory with fixed delay?
Great question. The idea is a delay line, the idea of a delay line is just that you have a very long fiber, and that long fiber will essentially store your photon there because your photon will take time to propagate through it. As we've seen, a delay line suffers from significant loss because you have an exponential loss when you propagate through the long distances. Therefore, if you want a short storage time, fibers are pretty good. But if you want the long storage times to the level that we're going to need for a global quantum internet, milliseconds or even seconds, a fiber would not be able to have a high efficiency. On the other hand, fixed storage time quantum memories offer a efficiency over time that scales much better than that of optical fibers. What I can say is that right now we don't yet have a fixed storage time quantum memory that offers better efficiency for a given storage time that is beyond that what a fiber can do. So we are still at the point of the technology that fibers are actually better. But that's not demotivating, that's actually motivating. We have a reference. We have to beat the delay line, and that's the goal.
QKD for long distance can also be achieved via terrestrial trusted nodes. What do you choose, satellite or trusted nodes?
I don't want to give an answer that is based on opinion, because as we know right now in our classical network, we are, we use trusted nodes whether we like it or not. Our information is stored somewhere, and there are people who have access to it, so we essentially trust a few big corporations to keep our secrets. So the idea of trusted node is something that permeates the information society, whether we like it or not. Now, in QKD, you have, and in particular, entanglement-based QKD, where you actually use the quantum repeater to distribute the keys and do not need any trusted nodes. The idea is that no one has access to your secret except from you and the person that you're communicating with. Therefore, whenever we're talking about QKD, I tend to stick to, okay, if we're using this, let's use it for real. Let's not introduce trusted nodes, otherwise you break the security that QKD is offering you, and then it's better to maybe not use it. I'm not saying that let's not use trusted nodes for the time being before the technology evolves to the point that we don't need them. Absolutely, let's do that, and that's what's going to probably propel the technology into its next stage. But from an idealized perspective, I would absolutely prefer to go fully untrusted node QKD with satellite connections. Again, because the satellite is not a trusted node. The satellite has, or at least if you follow our first webinar, the satellite has a source in it, a source of entanglement. And with entanglement-based QKD, there's no tempering of the source that you can perform that would leak information to a eavesdropper. Therefore, the satellite is not really a trusted node in the case of QKD from space. And therefore, I stick to that.
Well, even to echo this answer, from a discussion I had with a potential user of the technology, for the first generation of QKD, the prepare and measure, where you need to trust the satellite. Well, that person, who is in fact a leading voice in cybersecurity, was saying that for him it was easier to trust a node in space than to trust a node on the ground. That it was okay for a demonstration, but for real use case, an extra trusted node on the ground for that person, which is an international organization, was very difficult to give trust to a node on the ground for operational matter. After, it's always a question of requirement, also the level of secrecy you want, but I think it goes in the direction from the user side of what you say.
And that's an extremely good example of how the use cases are driving the platforms. You see, as a physicist, I have a certain interpretation of how or where to use trusted nodes. A user that you bring is much more likely to say, look, I can be flexible enough to allow for a trusted node in a satellite. And when I receive that information, then I can design the system to have a better platform to fulfill that use case. Maybe I was overthinking it, thinking that I would have to combine many platforms and spend a lot of money on it. But if the user is willing to be that flexible, then we can have a solution for him that is more efficient.
Thank you very much, Gustavo. I see, in fact, the clock. I think we have to close our webinar here, but it was an absolute pleasure for me to be here again. I hope for you also, Gustavo. Thank you on behalf of TNO for listening, and I'd like to take an appointment for next year. See you soon.